Hello. In this video I want to discuss further use of the bounds for the error term when approximating a function by its Taylor polynomials. And so just to recap, we have a real number a and a function f defined on some open interval I containing a. And if this function has an nth derivative which exists and is continuous on the interval I, then we can write down the Taylor polynomial Pnx for f about x equals a. It's given by this expression here. And of course the idea is that the Taylor polynomial Pn is supposed to be an approximation for the function f whenever x is near a. Now in a previous video we discussed error estimates for the approximation. So if you take some interval, say a minus d, a plus d, contained in the interval I where your function f is differentiable, and if you assume that your function has n plus 1 derivatives, and the derivative fn plus 1 is continuous on this interval from a minus d to a plus d, then we can get a bound for the error term en. Okay. So how does this bound look like? Well, if your derivative fn plus 1 is bounded in absolute value by m on this interval a minus d to a plus d, then the absolute value of the error en is less than or equal to m x minus a to the n plus 1 over n plus 1 factorial for x in the interval from a minus d to a plus d. Now let's see how we put this error estimate to use. Well, let's look at an example. Let's take the function f of x is 1 over x plus 1, defined whenever x is not equal to minus 1. Now, if we approximate f at 3 over 2 by the nth Taylor polynomial Pn for f about a equals 1, how large should n be so that we have an error less than 10 to the minus 4? Okay. So let's get our heads around what's going on here. We are approximating f at 3 over 2 using a Taylor polynomial Pn about a equals 1. Okay. And now we want to know, we're not interested in the actual value of the approximation in this problem. What we're interested in is how it should be so that our error is less than 10 to the minus 4. In other words, we want this approximation to be accurate to 4 decimal places. Okay. And now, what should n be? At least. Right. So let's see, how do we use our error estimates here? Well, the first thing we need to do if we want to use this kind of error estimate here, right, is we need to see what should we take this interval as. Well, let's see. Taking the Taylor polynomial a equals 1, and we want to approximate f at 3 over 2. That way, right? So we should move 1/2 that way, ending at half. Right? So this should be our interval. Right? Remember, we always take the smallest possible interval we can, because the closer you are to a, the better your approximations tend to be. Right? So we need to take our interval I as 1/2 up to 3 over 2. Now what should our m be? Well, in a previous video we proved the following. We proved that the nth derivative for our function f, this one, the n factorial over x plus 1 to the n plus 1. Of course, that's for x not equal to minus 1. So in particular, right, we need to look at the derivative fn plus 1. So that's going to be minus 1 to the n plus 1, n plus 1 factorial over x plus 1 to the n plus 2. And we're in any event interested in the absolute value of this. Right? And now the absolute value of this would just be n plus 1 factorial over x plus 1 to the n plus 2 for x in our interval I. Right? And remember, I is the interval from a half 3 over 2. So if we want to get a bound for this, so we want this less than equal to m, then we need to see what happens to that. Right? So let's have a look. So we take x in our interval I, which is from a half to 3 over 2. That's between a half and 3 over 2. 3 over 2 and 5 over 2. So plus 2 less than x plus 1 to the n plus 2 less than 5 over 2 to the n plus 2. So if we look at 1 over x plus 1 to the n plus 2, that's going to be less than or equals there. That's going to be less than or equal to 1 over 3 over 2 to the n plus 2. Bigger than or equal to. So if we go and we look what absolute value of fn plus 1 is, right? N plus 1 factorial over x plus 1 to the n plus 2, we see that absolute value fn plus 1 of x is less than or equal to n plus 1 factorial 2 over 3 to the n plus 2. Right? This comes from there. And this is true for x in our interval I. Right. So what is our m? Right. That's our m. Right. So our m is n plus 1 factorial 2 over 3 to the n plus 2. So our error bound for x in our interval I, what is our error bound? Error at nx is less than or equal to a, and our a is 1 to the n plus 1 over n plus 1 factorial. Now we just substitute in our value for m, and we get x minus 1 to the n plus 1. Right. So now in particular, remember, we're approximating f at 3 over 2 with the Taylor polynomial Pn at 3 over 2. Right? So that means we need to take x equals to 3 over 2. So what we have is that the error at x equals 3 over 2 is less than or equal to 2 times, right, now 3 over 2 minus 1 is a half, so 1 over 2 to the n plus 1, and that's going to give us 2 times 1 over 3 to the n, or if you like 2 over 3 to the n. And there we go. Now, how do we use this error estimate? So recall, what do we want to do? We want to find n such that, let's make that a little nicer, the error at 3 over 2 is less than 10 to the minus 4. Right. Now what do we know? We know that the absolute value of En at 3 over 2 is less than or equal to 2 over 3 to the n. So what can we say? If 2 over 3 to the n is less than 10 to the minus 4, then likewise the error En at 3 over 2 will be less than 10 to the minus 4. So what is it that we have to do? We have to determine how large so that 2 over 3 to the n is less than 10 to the minus 4. Right? We need to find this n. How large should it be? Now luckily, this equation is relatively easily solved, right? Because 2 over 3 to the n is less than 10 to the minus 4 if and only if the n is bigger than 2 times 10 to the minus 4, well, 10 to the plus 4. And this is true if and only if n is bigger than ln 2 times 10 to the 4. If and only if, when we apply our log laws, n ln 3 is bigger than ln 2 times 10 to the 4. If and only if n is bigger than ln 2 times 10 to the 4 over ln 3, right? Because remember, ln 3 is positive, and this is approximately, punch it in on your calculator, 5.752. Now remember, n is a natural number, so we have the error is less than 10 to the minus 4 if n bigger or equal to 6. So if you want an error of less than 10 to the minus 4, you need to take your n at least 6.